Okay. Hello, everyone. So we are going to start the fourth lecture today. In which the topic of this lecture is going to be broadly, so this lecture is going to connect naturally with the last lecture, and we are going to spend these 2 last hours describing the dynamics. So far, in the first 3 hours of the class, we discussed basically properties of the learning problem that one could even call like static, right? It's just we define functions, and we just ask the question, what are the properties of like cherry-picked functions in that space, right? And we saw that there were very different function spaces had different properties in terms of approximation and generalization. Today, in these 2 hours, we are going to focus on the dynamical part of things, right? So how can we actually define algorithms or trajectories that are going to find or move in that function space to find good functions? Okay, and so just to recall a little bit the objects. So what we had is the L that is a loss function. And then we had what we consider is now we're going to consider a function space F that contains functions. And let's assume that we have a procedure to visit this function space, right? So as in other words, we have a mapping that goes from some space of parameters to functions, the corresponding functions. So an example of that, we saw a couple of examples yesterday, where what we saw is, for example, that the space F2 that we described the other day were functions f of x that I can write as an integral representation of some neuron with some parameter times some coefficients with some measure, right? That was the basic space that we had, right? So in that case, the example of privatization is that, okay, I come up with a certain distribution over the weights. So these are my parameters. And once I have this distribution, I get the function, right? So in that case, the mapping would go from this distribution to this function, okay? So in general, what now I can, so we have a loss function that goes from L, goes from the space of functions to R. So this is the function that assigns how well we are doing it. And now we have a mapping that goes from the space of parameters that we can call, here we can call this parameter belongs to maybe like a big parameter set. We have another mapping that goes from here to here, right? And so we can call this mapping, we'll be using this notation today, that's phi, right? So I have an element here. From here I define phi of theta, that is a function, and then I can evaluate this function through L of phi of theta. And of course, if you remember from the first lecture, the first objective in machine learning is to solve the empirical risk minimization, or with or without regularization. That essentially involves minimizing this loss over function space, right? But now, because we have a way to parameterize this function space, it's very natural to express this minimization problem in terms of parameters, right? We have parameters, and now we can call this function just by definition can be the composition of L with phi. Okay, isn't it just to make sure that the notation is not too heavy? Yes?
Phi of theta over there is the same as the f of theta on the left, in the left?
Where? Here? No, so basically, yes, sorry, here is, I'm realizing that I'm using theta many times over. Let's just rename the thing in case that it's not confusing. Let's call this Z. Let's call this Z, and let's call Z here.
You see the mapping from theta over there?
Yes.
To phi sub theta, to f sub theta?
Oh yeah, so you're right. So that would be phi of theta. Thank you. Okay. So now, today, the main focus will be how can we approach this problem? How can we solve this problem? So there's one simple case where this problem should not be very scary. And just to remind what are the properties that we can expect from this function L. Let's put L. Let's define it as, just to make our lives a little bit easier. Let's put the simplest loss function one can think of. Let's consider L of f to be just the mean square, right? With some f star. And this distance, if you remember, this metric is with respect to the data distribution, right? But in your mind, think about this L function. L is like a distance, like an Euclidean distance measured in some data space. Okay, so there's one case where this problem should not be very scary. That is the case where when phi is linear. So what happens when this mapping, I have basically a linear parameterization of functions. Should I be scared about this problem? So let's write it again, right? So that would be like phi of theta minus f star. And I need to minimize with respect to theta, right? Because when this mapping is linear, this looks like is a least squares problem. It's a least squares problem in functional space. So in particular, we can leverage all the machinery that you studied in the Convex Optimization class, right? So we have, in particular, we know how to reach the global minimum of this function, and we understand the rate at which we can reach the global minimum, and we have actually matching upper and lower bounds, right? So we have a very good understanding on how hard it is to solve this problem. And just a precision, so in that case, we have a least squares in functional space. So least squares in functional space, in fact, is completely directly related to learning in the functional space that we described yesterday that gives here the Hilbert structure, right? So this, doing least squares in function space is equivalent to doing what's called like a kernel learning. Okay, as we saw yesterday. Okay, so what you have in mind is that when I have to solve, when I have a linear parameterization of like a linear functional parameterization, and I learn over the linear parameters, right? I'm finding this in that case that would be this distribution over the neurons. I'm essentially relying on a kernel method, right? If you remember, in this particular case, the single hidden layer neural network, the corresponding kernel, if you remember, was given by k of x prime, the expectation with respect to the data to the prior distribution of the corresponding neuron. Okay, so once I have a linear parameterization, right, the terms, the functions that I use as generators define a kernel. Okay, so that's so we are here in convex world, right? Things are okay. But now the question, obvious follow-up question, is what happens when phi is nonlinear? So of course, formally, I can still write the same object, and I can try to minimize this objective. But the main consequence of that is that in generically, we arrive at a non-convex problem. Okay, so that's, in a sense, the, well, I mean, I didn't anticipate, this should not come as a surprise, but one of the important, like I'd say, like the main reasons why optimization is so crucial within the study of deep learning is precisely because we have to understand, we have to deal with this non-convexity. So what happens when you have a non-convex optimization problem? Well, probably you have seen, or you have tried to imagine, like, visualize what would be to optimize a function that is non-convex. So of course we can start by these kind of toy low-dimensional drawings where you can already see that now specifying what I need to do becomes much more brittle, right? I need to do much more effort to specify what is my model going to do, right? Because in convex optimization, so probably you saw the major results in the lectures, but for example, what is the role of initialization? When I have to solve a convex problem, how is my behavior influenced by initialization? But, so in other words, you could say, at worst, you are going to wait a little bit longer, but I can certify that it doesn't matter, right? Here, probably obviously the answer cannot be the same, right? So if you're in a convex world, like, I cannot certify you anything. I mean, I can tell you maybe, if the thing didn't go, if in one run you didn't succeed, maybe I could tell you, well, why don't you try again, right? You start from another place and you try again, and maybe you try again, and again, and maybe eventually you are going to find a good solution, right? This doesn't seem very rigorous, right? Very robust. So in a sense, that's what I meant by this. We have to deal with something that becomes a little bit more unstable, a little bit more brittle. And so we can have local minimum that are not global, and in general, in high dimensions, we can have, so we have a poor, what's called poor local minima, and we can have also something that is called like a saddle point, which is I'm probably not going to be able to draw it in the board, but well, if you know how a saddle looks like that's a point where, like, first, like, it's a stationary point. It's a point where the gradient of the function is 0, but where locally there's still a direction to go down, except that my gradient method is not able to find it can get stuck here, right? So saddle points are bad, etc., etc. And so one of the things that is very important for us is that if you're in a linear model, right? If you're in the linear model, the behavior of the generalization of your learning machine, right? So I can specify how well my model is going to generalize, is completely determined by the kernel, right? So in other words, the optimization algorithm that I use to find this minimum has no role to play in deciding if my model is going to work well or not, right? In a sense, the performance of my model, in a sense, is robust against different choices of optimization. This is not the case in general, right? As we will see, there's the same model, the same algorithm, gradient descent. It might generalize very well if I initialize the parameters at some point, and it might have very poor generalization if I choose a different initialization, right? So that's why this problem is at the same time messy and fascinating, right? Because now if we want to understand, like, approximation in functional space, we need to deal with the optimization, right? We need to, in a sense, the problems are kind of mixed one into the other. So let's go into a little bit more in detail into the performance of gradient descent. So now let's just really spend the rest of today's lecture and following lecture mostly focusing on this algorithm, the gradient descent. So gradient descent, and I will always assume I'm not going to spend a lot of time discussing the step size. Okay, so let's first assume that the step size is fixed, constant. So what is the definition of gradient descent? Is my next point in parameter space is going to be the previous point minus this step times the gradient with respect to the parameters of the loss that they have. Okay, so I'm writing it in a lot of generality, meaning that in stochastic gradient descent, in gradient descent, these can be a noisy version of the loss. Okay, so depending on which flavor of gradient descent I'm using, I might be using like the empirical loss. If I'm using the whole batch, or I'm going to using some, like some. Did you cover stochastic gradient descent with SEB? Okay, so that would be one possible flavor, is that you are using only part of the data. But for us, you should not worry too much about that, right? So just think for now that you're using the vanilla gradient descent. Okay, so we can even use the loss. Okay, and so obviously I'm not gonna spend much time developing this term, but because this, a priori, this function as we define it is the composition of two functions, right? And even more generally, this mapping phi, which maps parameters to the function, as we described yesterday, it can itself involve composition of several things. In particular, if I have a deep neural network, this phi is going to itself be a composition of several functions, right? But I guess that by now all of you are comfortable by, comfortable computing gradients with respect to the parameters just by applying the chain rule, right? And so the chain rule is also known as the backpropagation, right? So the back. So this is what's involved in computing this term. Okay, so so this is an algorithm that is kind of the simplest one, but let me, a very simple one, but let me simplify it one step further, right? So let me remove from the picture the step size. Okay, so now let's try to see what happens as the step size goes to 0. So as the step size goes to 0, we can, we transform basically a discrete time system into a continuous time, right? So as the step size goes to 0, we go from gradient descent, and I believe that this is something that you also described a little bit with SEB, from gradient descent to gradient flow. Okay, and let me, and again, we are also mostly going to be interested in describing and trying to analyze the gradient flow for these problems, right? So obviously there's a gap between the two. So if you want to transfer all the things that you learn in continuous time back to discrete time, you need to make this, obviously you are making this, you are only studying the problem in the regime where the learning rate is very small, right? So there is just I would like you to be aware that everything that we are saying is in the disclaimer in the regime where the step size is very small. So now let's look at the gradient flow. So gradient flow, again, the trajectory, the dynamics in the parameter space are going to be given by the minus the negative gradient with respect to theta of theta t. And let's look at what happens with this trajectory. So this is a trajectory that it's done, that is happens in parameter space. So this is the parameter space. And as we said, we have a mapping that goes from parameter space to function space, right, with phi. Right? So we start with some parameter, and then the gradient flow is going to define some kind of trajectory here. And this trajectory is going to be mapped through the mapping to another trajectory here. So what are the dynamics of this trajectory? So I can define phi of t, but I can define it as phi of theta of t. So what is the dynamics of this space? So again, what is this? This times this, right? So I can just push the dynamics by applying the chain rule again. Okay, and what is this time derivative? Right, it's by the gradient flow. So at the end, what do you get? And then you get the loss prime at phi empty. Okay, so here the only thing I did is that I applied the chain rule again on the computation of this function. Okay, so now let's try to interpret this trajectory. There are basically two ingredients. There are two objects here. And there's a minus that I forgot. So what is this object? So this object, we are going to call it k at time t. And let's see what is the description of this thing in coordinates, right? So this is, you can think it as an operator that has two arguments, right? That has, these are 2 points so these functions that go from x to rd, x to r, excuse me, and these are two coordinates in that space. So this, by definition, is going to be the Jacobian, like the Jacobian of phi theta t evaluated at x with the Jacobian of phi of theta of t evaluated at x prime, right? So here this is a kind of a matrix, and so the coordinates in this matrix are just the dot product between the row of this vector and the corresponding row of this vector. So what is this thing telling me? Is that at every point in time, here I'm at a location phi of t, right? So I have a function that is what we call phi of at time t. Yes?
Those 2 points are different, right?
X and x prime?
No, the previous line. The d phi transpose and the d phi, those are different phis, right? Because you...
No, they're the same.
But you define phi of t as phi of t2.
Oh, sorry. Yeah, sorry. No, this is just basically the function at time t. Okay? It's an overload of notation. I assume that I agree that this is a bit, the notation might not be very clear, but it's basically the point, like it's the Jacobian of the function at time t. Okay? So it's d of phi evaluated at theta of t, if you want. That's more precise. Thank you. Okay, so what this thing is saying is that I'm at time t. I'm going to have a function here. You have a question?
I'm just curious, so this k, what are the gradients with respect to?
With respect to theta, yeah. So I'm at time t, I have a function here, and my target is f star, right? It's a function that is somewhere there, right? So if I'm using the L2 distance, and you were free to move in function space, what would be the trajectory of gradient flow? If you are here, let's assume that you could move freely in function space, and this is your target. What would you do? You would go straight, right? You would take this trajectory. So this is exactly what this term would be telling you, right? This is exactly the difference between phi of t and f star. But now you are not free to move in function space, right? You are only moving in function space through this parameterization. So what is the effect of this parameterization in the dynamics? So basically, this is just multiplying. It's kind of a change of variables, right? A change of metric. So this is the kernel. So this change of metric is given by a kernel that basically modifies the trajectory because you are not moving in the intrinsic space. You are only moving in function space through a parameterization. Okay, but this is an important kind of consequence of the fact that we have no algorithm that could simply move in function space, right? We have to visit them through some parameterization. Yes?
So distance in the function space is defined through the kernel.
Sorry again?
Distance in the function space is defined through the kernel.
No, here I decided to use this metric, right? So basically, I have two functions. I can define the distance. So the dot, like the metric in between two functions. That's a good point. In L2 xv is the expectation with respect to my data distribution of f of x times g of x. Okay, so this is actually what we can call. So this we can call it the tangent kernel. Okay, so it's a tangent kernel because you can really see it as a locally, what is the change of metric that is incurred by the parameterization at time t, right? So of course, this is in general, this is going to be a kernel that depends on t, right? Depends on where I am, depends on the value of the parameter. Yes?
Sorry, so what's x here? And how does phi now take theta and x, whereas phi
This is because these are a function, right? So this is a function. Phi of theta is a function, right? So if it's a function, it takes an argument x. So f is a function space.
It looks like phi there is a function of one argument, theta.
Yeah, well, I mean, it's just because I'm going to simplify, but in fact, you can write phi of, okay? And now this is a function, so it is, I can evaluate the function at point x, right? So I can write phi of x, phi. So if you prefer, well, I mean, I could rewrite everything by having the two arguments, but I really don't like, I don't like this notation. I don't know. I prefer just to, but sorry, I mean, if it was not, so is it clear now?
So that's something in the training set, like some data point.
Yeah, so think about this example before, right? So I have neurons, and neurons have two arguments, weight, and they admit as an input. And then if the context is clear, I can just see this as an object, right? That is a linear combination of parameters, but I can always evaluate this object at one point x. This could be like the input image. Okay? Is it clear? Good. Yes?
Sorry, I think you already said this, but what exactly happened to ddt of theta? Like, what's it getting replaced by? Just one line up. Yeah.
Yes.
So we had ddt of theta t, and then what did it get replaced with?
Oh, this is just the Jacobian of this mapping evaluated at the coefficient where at the parameter where I'm at, right? So this mapping phi goes from parameter space to function space. So the Jacobian of this mapping, I can evaluate it at one particular point. And this is the same. It's the same object, right? Because it appears twice. It appears once because so it's this idea of the change of metric, right? So when I have when I look at the trajectories, right? I look at the trajectory in that space, but because the algorithm looks at this space, first I have to go there and I pay the adjoint of the Jacobian once, and then I want to see how this map looks back in the function space, so I have to pay a Jacobian again. That way I have the Jacobian transpose times the Jacobian. Yes? This is
I was expecting to see negative gradient.
yeah, it's a negative.
Okay.
I mean, the negative gradient comes from here. Right? Only Venus. So this is an elementary computation, but I recommend that you do it on the back of the envelope, because it's really something that, in a sense, is easy, but you have to do it once to be really comfortable and be convinced, right? I mean, there's really nothing magical here. I'm just doing the chain rule. Okay, it's really the change of variable. Okay, so this is called the tangent kernel. And a priori, so at this point, the only thing that you should retain from this is that it's an object, it's a kernel that is time dependent, right? So if I move in parameter space, a priori, for generic parameterization, this object is going to move. Okay? So, but in fact, there's and this is where kind of kernels become back in the game in the deep learning literature, because there's an interesting phenomena happening. And what is this phenomena? Is that in some conditions, the situation becomes much easier. And the situation in which this description becomes simpler is something that maybe you have heard or you have read about, that is the so-called, oh, this is very wet. Sorry, I'm not sure this is going to go well if I start writing here. I mean, I will just use the liquid to do as much as I can. Okay. Okay, should be okay. Okay, sorry. Okay, so there's one situation in which this thing becomes a bit simpler. Is what's called the over parametrized regime. So who has heard about this word? Okay, that's some people, but some of them not. Okay, so let's try to understand or like unpack what this means and what is the impact, how it relates to the story so far. So let's just look at the simple example where my model now, and I'm going to explicitly write it with the argument. Okay, I'm going to think I'm going to consider the single hidden layer model again. Single hidden layer. So that's going to be, and let me choose that scaling, right? So I have m units, and I'm going to compute this sum from 1 to m of. I'm going to use G because it's going to use all the time. Where the initial parameters of these neurons are drawn IID from some initial distribution. So let's look at the kernel in that regime. Okay, so this a priori is a model that depends on the number of neurons. Let's study what happens when I over-parameterize. What does it mean over-parameterize in this context? So m grows, right? So let's see what happens as m grows. So let's compute this kernel. So what is this dot product? Okay, so you look at the Jacobian with respect to the parameters, right? So this, by the linearity of the gradient, what does it become? So I have.
The thetas, are we optimizing with respect to the thetas?
Yes.
So why are they drawn from a distribution?
No, this is at initialization. So let's, yes. Okay, so that's the time 0. Good question. So I have this one square root of m. By linearity, it would also be in this term. It would also be in this term. So what do I get here? I get 1 over m. And now because I have a different parameter for every term, in the Jacobian it's going to be its own coordinate. So when I do the dot product, what I'm going to get a sum from I equals 1 to m of the Jacobian of this little function, now with respect to its own parameter, of g of theta I x times the Jacobian with respect to the same parameter of g of theta I x prime. Right? Everyone sees that? And so what will happen as m goes to infinity? And we're not going to formalize this a lot, but just to get you the intuition. So this is an object, right? It's a kernel. But it's a kernel that is random. Why is it random? Because these things are random, right? I just consider the random object. But good news, all these things are IID, right? So basically I'm doing an average of IID objects. So these are random kernels, but I'm just averaging a bunch of IID random kernels. So what does this thing converge to? This thing converges to a deterministic function, right? It's a deterministic kernel that we can call k infinity of x prime, which is nothing else than the expectation with respect to mu0 of phi of theta x tan phi of theta of x prime. So with this parameterization, so with this scaling, it's a choice, in a sense, I can add parameters. I can add neurons into my layer, and the system, the model, converges to at least the kernel, right? The object that appears here admits a limit, right? As the number of parameters goes to infinity. So this is, it's nice. Yes?
Only for one xx prime and not for all of them together or something like this.
Yeah, but if you look at so we go through the fine print, but you can get uniform convergence under some assumptions, right? And so this kind of observation is not new at all. So you can, first of all, you can get like a very good reference in the nice paper by Rahimi and Brecht. They already computed this thing, and there's actually another paper that has a very, very fine-grained analysis of these random kernels. So this is actually a random kernel, right? And basically what we're saying is that this random kernel can be used to approximate this deterministic kernel, right? So typically the people go the other way around, right? Is that you would like to learn in that kernel, what is an efficient way to do it? Well, you just sample random features, right? Here what we say is basically just this equivalence. And there's another paper by Francis that is called On the Equivalence between random kernel expansions and quadrature rules. It's from 17. That also gives you a little bit more quantitative results on this, right? But now let's not spend too much time. Okay, so this is actually, not new. I mean, this paper is from 2008, right? And people have been aware of this kind of equivalent. The thing that was a bit less obvious and that kind of boosted a lot the interest in the deep learning community and kernels is a phenomena that is maybe a bit less intuitive, right? And this is captured by this theorem from Jacot, Engler, and Matthew Wyatt from last year. This is maybe something that you heard about, this neural tangent kernel. So what does the theorem say? Is that not only this system, right, this model, at time 0 has a limit that basically is a deterministic kernel. This kernel, this kernel k infinity, is actually valid. So in other words, if I go back to this model, what I know is that for all times, right, as m goes to infinity, uniformly over compact, what I have is that this kernel that we described before, so theta of t x with the gradient of theta of t x prime, that's what we call kt in our notation. In fact, this kernel converges to this kernel. There. As n goes to infinity.
So this is just the initialization, right?
This is the initialization.
And then kt is the time derivative of the kernel?
Kt is this object here. So what is the surprising fact? And this is obviously, this is 4. So what is the surprising fact here? Is that this thing a priori depends on time. So this object a priori should depend on time. This thing does not depend on time. Right? So this is the thing that is remarkable. And it's a bit saying, okay, maybe we need to reassess what's happening here. So we started from a model that is nonlinear, right? So first observation. obviously, if my parameterization phi is linear with respect to theta, does this thing depend on time? Why not? Because if this thing was linear with respect to theta, when I take the gradient with respect to theta, the dependency on theta disappears, right? So it should not, the time should not depend on that. So the fact that this object does not depend on time, it kind of smells like the model behaves like a linear model, right? Because this is exactly what you would expect with a linear model. So what this result is saying is that as a consequence, under the scaling, that under what I call the 1 over square root of m scaling, phi of t, or phi of theta, behaves like a linear model. And this result, I just illustrated here for simplicity when you have a single hidden layer. But if you look at the result, there's nothing particular about the single hidden layer. It's also valid for generic deep neural networks. Yes?
You see this as some sort of embedding of a really weird manifold in a very high dimensional space with low distortion? I mean, is this what like the number m means in this case?
Oh. I'm not sure I really understand what would that. What,
linear, so what does it mean almost linear?
Right. That's a very good question. In a sense, that's what we are going to be focusing in the next 20 minutes. So what does it, now we really need to understand what's going on here, right? What does it mean that a nonlinear model, if I take this limit, we don't really understand what is the link between this m and the linearity of the model, right? It's like we're constructing a nonlinear function that is a sum of many functions. And somehow, even if these individual terms are nonlinear, I'm scaling the thing in such a way that the overall model only captures, only uses the linear part of this thing, right? So in a sense, the nonlinear properties of the model that are, this thing can be definitely very nonlinear, are not being seen through this scale. So that's something that we'd like to understand. Yes?
So what's the consequence of that for gradient flow? Does it mean that gradient flow will...
Good. So now let's go back to gradient flow and see what it would mean. So what is gradient flow going to do in that case? You just have like the derivative at time t is minus a kernel times the difference between t minus f star, right, if I use the square loss. So this is an object that is now fixed. So probably you have seen it, maybe you have seen this during Sebastian's class. So this is the dynamics of a least squares problem. And not only that, when I am in this over-parameterized regime, I can make it such that this kernel is non-singular. What does it mean? It means that the null space of this kernel is a zero function. So in particular, I have a linear system. The dynamics. So this really looks like an ordinary differential equation where the singular values of this guy are away from zero. So what is another very important consequence? Thanks for the remark. Is that what is the convergence that I should expect in that case? I'm trying to do gradient flow on a least squares problem that is strongly convex. Like linear convergence, right? Exponential, right? So I have basically linear convergence. So it seems that for now, suddenly, deep learning is not so complicated, right? Because I'm just saying, if I make the model sufficiently wide with that scaling, the dynamics, the optimization of this problem is going to essentially feel like just solving a kernel model, which has like probably the best you could dream of in terms of convergence. Yes?
In the definition of t infinity, there's a theta, right? So is that a theta of t? It's not theta of t over here.
Here? No, this is a fixed curve. So this is an expectation with respect to theta. No. This is the nice thing, right? This is the surprising thing, right? So whatever I do at initialization is going to stay there. So the dynamics only use the initial distribution over parameters.
That theta has to be there. Like phi
Which one?
Like phi theta t.
Here?
Yeah.
Well, no, because this is what the algorithm is doing. So I'm running gradient flow. So you give me the model, I just run gradient flow. So gradient flow defines the trajectory theta of t. The statement is that this object that appears in the dynamics here, when m is very large, doesn't change. That's what this statement is saying. Yes?
I feel like you're saying it's hiding all of the data. Like there's no dependence on the data.
There's no dependence on the data. The only place where the data appears, and that's a very good question, is precisely what I said about what's called like a single, the fact that the kernel is singular or not. So the fact that I can solve, so in other words, what the fact that I have finite amount of data, what it will mean is that I can invert this system, like that this system has no null space.
Just to clarify, so you have these inner products written, and
Yes.
these are not, are those over the data
Yes,
distribution?
these are over the data distribution.
For KT as well?
Where do you see? No, this is a dot product. This is actually, yeah.
It's
So
not
this,
over the data distribution.
no, this is not over the data. This is over the parameters.
That dot product is just a normal vector.
Yes.
Dot product. So in the data comes in when you have this K operator, and then there's some
Exactly.
sort of distribution.
Exactly. Okay. Very good. So I have 15 minutes left. So let's now try to unpack or try to interpret and analyze this surprising phenomenon that, as I said, is really giving us the impression that deep learning is easy, or at least partial impression that the deep learning is easy. So this is so now we are going to forget for now about the neural network for a second. We'll come back there very soon. So now we are going to describe what Leonid Shiza and Francis Mack call this lazy training dynamics. And this is a very beautiful paper by Shiza, Oyalon, back 19. So for this, we can, again, just assume that I have a mapping that goes from parameters to functions, and this mapping is differentiable. And what I suspect, and I have, so this is the initial condition. And what we suspect is that this model that is nonlinear, in some regime, what we saw is that it behaves as a linear model around the initialization. Right? So now let's define the linearized tangent model. Okay, so we can call it phi, and this thing is not working. So this should work. Okay. Of theta, which is the function. So again, I'm going to write it as a function so that it's more clear. It's phi of theta 0 at x plus theta minus theta 0 times the gradient with respect to theta of theta at theta 0 and x. Okay, so everyone sees why this is a linear model now with respect to theta? right? Theta only appears here, right? So this only depends on the theta 0, and this only depends on theta 0. Good? So the question that this paper studies is when are these two models similar? In the sense of, if I start at the same point, and I follow dynamics, I follow the gradient using this model or this model, I'm going to be visiting the same functions as time, right? I'm going to be moving the path that I will be doing in function space. When are these paths going to be similar? This is not working very well either. Okay. So again, we are going to see this. Okay. So let's again define. Sorry if I change the notation, but I think it's the same notation. Right, again, phi of theta. And let's assume that the error that we do at time 0 is that we are not at the global solution. Let's assume that at time 0 we are not at the global minimum. Okay, so when we do a gradient step, when we update when we move away from theta 0 by applying the gradient step, so a gradient step will give, again, theta 1, which is theta 0 minus eta, the gradient of E at theta 0. So now what this result that we described before, what this result told us is that as we move in the trajectory, the change in the kernel was much smaller than the change in the progress that we make in the loss function, right? Because as we know, the loss moves very fast, right? If we are in this regime, but the kernel, this linear object, does not move very fast. So let's try to, in that sense, to compare what is the change that we make in terms, what is the relative progress that we do in the function versus the relative change in the corresponding linear model. Okay, so we can say that the relative change in the objective, what is it? Would be like something that we can define like this, theta of E. That is, what is the energy that we have after we made the step with the energy that we had at time 0 divided relative to the initial loss. So what is this approximately? What is the approximate relative change in function? Right? So I can do Taylor of E around theta 0. So I can approximate this as being the energy at theta 0 plus the gradient of E at theta 0 times the difference. And what is the difference between the two? Again, something that depends on the gradient. Right? So this is more or less the step times the gradient of E at theta 0 times the gradient of E at theta 0. So one of these terms comes from the Taylor decomposition of E, and the other one comes from this difference between the two, right? Which is, again, this is divided by theta 0. And what is the relative change in the linear model, right? In the tangent model? So in other words, we'd like to see how the Jacobian structure changes as we update. So we can call this the difference into the Jacobian of phi. So we have to evaluate the Jacobian of phi at theta 1 minus the Jacobian of phi at theta 0. Relative to the Jacobian of phi at theta 0. And again, if I do Taylor, well, let's assume that this model, that this thing is smooth. I can do Taylor decomposition. What do I get? I get something that is controlled by the step size times the norm of the Hessian of phi at theta 0 times the gradient of the, like the difference that I do, the gradient on the loss at theta 0 divided by the original quantity, right? Okay, so this is really nothing, there's really nothing complicated here. I'm just doing the Taylor development. So somehow the phenomena that this neural tangent kernel captured is that it's something that can be understood, can be expressed just by comparing these two quantities. So what this phenomena that the previous theorem captured is the fact that there's one relative change that is much bigger than the other. Right? So what this paper, what the tangent kernel described is that the relative change in the Jacobian, in the tangent model, was much smaller than the relative change in function value. Okay, so in other words, if you just rearrange the terms, just making sure that I'm not doing any mistake, this is equivalent, if you just rearrange the terms, to asking to the following phenomena, which is the ratio between basically the Hessian and the Jacobian of the model is dominated by the gradient of the energy at time 0 by the function at time 0. So this might look like a little bit esoteric, but let's now, again, in particular, when L of f is a squared loss. So when the loss is a squared loss, we can explicitly compute this term, right? So in that case, the Jacobian of v at theta 0 is what? It's just difference between. So this is just the Jacobian of this minus f star. This becomes the difference between phi of theta 0 minus f star times the Jacobian, is of the same order, the Jacobian of phi at theta 0. Right, so in that case, what we have, well, we can define, and this will be the last slide, so we can, at the end of the day, we can define what we call like the relative scale of phi at point theta. We can define it as k of theta, of k phi at theta, to be the value of the initialization, phi of theta, minus f star, times the ratio between the Hessian of phi at theta 0 divided by the Jacobian of phi theta 0 squared. Okay, so just this is the definition that we use. And so what we are saying is that this property that this will dominate this, in that sense, is equivalent, so lazy is implied or happens when this relative scale, theta 0, is going to be much, much smaller than 1. Okay, so this is just rearranging these terms. So I take this approximation, I put it here, and I rearrange the terms, and you get like a pretty easy condition that involves just 3 quantities, right? So this relative scale contains 3 terms. What is the error of the model? What is the distance of the model to the target at time 0? So basically, this is the error at time 0, right? And then, what is the ratio between the norm of the Hessian, so this is kind of a curvature of the model, divided by the square norm of the Jacobian. Okay, so it's like kind of the norm of the second derivative divided by the square of the norm of the first derivative. Okay, so and just to finish today's lecture, why is this called lazy? That's the question. Why do you think this is called like a lazy regime? Where does this name come from? Okay, so it really comes from the fact that in this regime, I don't need to move too much to find the global minimizers of my energy. Why is that? Because what we just saw is that if I pretend that my model is like acting like a linear model, and this model is overdetermined, I get linear convergence. In other words, it's very easy to take the energy to 0, right? Because I just follow, I know that the linear model has exponential converges exponentially fast to the solution. So this lazy regime essentially describes the fact that even if my model is nonlinear, I can manage to find global solutions of the energy very fast. So I don't need to move too much to find these solutions. So you might think that this is it's a good thing, right? Oh, it's very, in a sense, I managed to find a global minimizer super fast. And you said, well, this was the whole point, right, of machine learning, is try to optimize complicated laws. Well, we'll see in the last lecture why this is not always a good idea, right? It's not always a desirable property. So we are going to see this in the last lecture. Thank you.